Hello, welcome to my talk on Bernoullis equation for conventional inviscid flows. In this talk, I will introduce briefly how our pioneer fluid dynamicists managed to solve the fluid dynamic problem step by step before Bernoulli's principle, and thus the Bernoullis equation, which firstly linked the fluid pressure and the fluid velocity together, the most important relation for fluid dynamics. In modern fluid dynamics, Bernoullis equation may be the most used equation for both engineering applications and in research. In this talk, we will see how the conventional Bernoullis equation can be derived for the general inviscid flows, which is derived based on Euler equation, the universal fluid dynamic equation for inviscid flows. And we will also see in deriving the conventional Bernoullis equation, some assumptions must be applied. For instance, the conventional Bernoullis equation is only correct for steady inviscid flows. Let's first have a look at the understandings to fluid dynamics before Bernoullis. Aristotle, in about 350 BC, he described the fluid as a continuum and suggested that the body moving through a continuum would encounter resistance. Archimedes, in 250 BC, he proposed the law of buoyancy. A body immersed in a fluid experienced buoyant force equal to the weight of the fluid it displaces. And he also initialized the understanding on fluid pressure. In fluid, each part is always pressed by the whole weight of the column perpendicularly above it. In about 1500, Da Vinci noticed the law of continuity, that is, the mass conservation, and he also stated the resistance is directly proportional to the area of the body. And Galileo was the first to formulate the fluid resistance, which varies proportionally to the density of the fluid. And he tried to build the relation of the fluid velocity and the fluid resistance. But he wrongly concluded that the resistance is proportional to the velocity. In the modern understanding, the resistance is proportional to the velocity squared. There were three famous experiments for understanding pressure and atmospheric pressure, including Torricelli's vacuum experiment in 1643. He could measure the atmospheric pressure and create a vacuum. And the barrel burst test by Pascal in 1646. He created the pressure in a long vertical tube. Large pressure caused the barrel burst. And he also proposed the Pascal's principle, which is widely used for engineering applications, such as we see use the Pascal's principle to lift a car slowly and easily. And in 1656, in Marburg, the hemisphere experiment, the two hemispheres put together, and the air inside was taken to make a vacuum in the hemisphere. In the experiment, 16 horses used, 8 on each side, to try to pull a part of the hemispheres, but it not separated. Based on their calculation, there was 20,000 newtons force acting on the hemisphere. And in 1687, Newton published his book, Mathematical Principle of Natural Philosophy, in which the famous Newton's second law of motion provide a fundamental equation for fluid dynamics. Euler established the fluid dynamic equation, namely Euler equation, which is the foundation for the complete fluid dynamic equation, Navier-Stokes equation. And Newton also defined the viscous stress for the fluid, the Newton's law of viscosity. Here, this is the principle for defining the viscous stress. Newton was also the first to theoretically verify the fluid jug is proportional to the velocity squared. And only Peter invented Peter tube in 1733, which is a simple device used for measuring fluid speed. Today, Peter tube is still widely used in engineering in the measurement of the fluid speed. However, we must note this invention was before Bernoulli's principle, which was published in 1738, and the Bernoullis equation, derived by Euler in 1752. So we can see, before Bernoullis, the Bernoullis' father, Johann, and the son, Daniel, the important relation between fluid velocity and the pressure has not established. But this relation is the fundamental relation for the fluid dynamics. Here come the Bernoullis' father and son. Daniel Bernoulli, the son of the Bernoullis, published his book Hydrodynamica in 1738, in which he initialized the pressure-velocity relation, named Bernoulli's principle. Pressure decreases when the fluid speed increases. He also drew a picture in his book as this. However, if we use this drawing, the Bernoulli's principle can be more easily to be understood. Here we use two different pipes for the fluid. In here, the large pipe means a smaller velocity, so the pressure here would be smaller than here, where the fluid velocity is very small or zero. And for the smaller pipe, the velocity V2 is higher than V1, and the corresponding pressure in this small pipe would be smaller, so H2 is lower than H1. It should be noted both Bernoullis had attempts to solve the problem, many based on the energy conservation, while a more general solution for the unsteady quasi-one-dimensional flow was derived by the father, Johann Bernoulli, in his book Hydrodynamica, published in 1743. See the reference given in here. In modern fluid dynamics, Bernoulli's equation is regarded as the integral form of Euler equation. But in the history, Euler derived both Bernoullis equation and the Euler equation, but in an order of Bernoullis equation first in 1752, and then Euler equation in 1757. However, Bernoullis equation is always derived from Euler equation. Firstly, Bernoullis equation is valid only for inviscid flow in the general form. This is same as the Euler equation, which is the universal fluid dynamic equation for inviscid flows. Euler equation is given in this form. Here, the vector F is the body force per unit volume. The conventional Bernoullis equation can be derived under the following conditions. The first condition is the flow is steady. Therefore, the term of the differentiation of the velocity vector with regard to time is 0. So we have the equation as this. And the body force must be a conservative force. The most applied conservative body force is the fluid gravitational force. In the Cartesian coordinates, see here, with Z positively pointing up, the body force can be given as this, and the expression given as the gradient of the function here. So this means the gravitational force is a conservative force. There is one difficulty term for the acceleration, the convective acceleration, but we can employ the vector calculus identity here. So if we take the vector A and B same as the velocity vector v, then the vector calculus identity can be expressed as in this form. So we can calculate the convective acceleration this term given by this expression. And we change the order of the cross multiplication for the vector, so we have the expression as this. As such, the Euler equation can be written in a form as this. Now we consider a special case on a fluid streamline. So the equation would be given by this differentiation form. And based on the definition of the streamline, we can see on the streamlines the vector ds has the same direction as v. Therefore, the core of the velocity vector cross timing the velocity vector would be perpendicular to the velocity vector v, since if we take the core of the velocity vector as an vector. So we can see in this equation, the last term on the left-hand side would be 0 because the vector ds is same as the vector, but this term would be perpendicular to the velocity vector. Therefore, the dot product of these two terms would be 0. And then the equation can be expressed as this. Here, we must note the density ρ and the gravitational acceleration g are both constant. Otherwise, we can't obtain the relation as this. And obviously, we can integrate this equation. and obtain the relation as this. Here, C1 is the integral constant, which can be decided for different situations. So in here, we can see for the general Bernoullis equation, the flow must be inviscid, incompressible, and the body force must be conservative, and the Bernoullis equation is valid only on the same streamline. In this slide, I will use the Bernoullis equation to explain the Bernoullis principle. See this picture here. So we use two different sides of the pipe, the large pipe here and the smaller pipe here. So for Bernoullis equation, as we derived before, it is given as this. Here, C1 is the integral constant. And if we take the bottom of the tank as the reference, so this term would be a constant. Therefore, the Bernoullis equation can be written as in this form. Here, C2 is a new constant. Now, based on continuity equation, we can easily see the velocity V2 here in the small pipe is larger than V1 here in the large pipe, which is larger than V0 in the tank, which would be very small or zero. Therefore, we can see in the tank, the flow velocity V0 is very small or zero. Therefore, the corresponding pressure P0 is high, which is indicated by H0. In the large pipe, the flow velocity V1 is larger than V0. Therefore, P1 in the large pipe would be smaller than P0. That is, H1 is lower than H0. And in the small pipe, the flow velocity V2 is highest. Therefore, the corresponding pressure P2 is the lowest, as shown by H2 here. This is in accordance with the Bernoullis principle. The pressure decreases when the fluid speed decreases, and this can be seen from this equation. When the velocity is increased, the pressure P must decrease, so to make this together as a constant. So from the conventional Bernoullis equation, we can see we have applied following assumptions. The flow is inviscid, so the corresponding governing equation is the Euler equation. The flow is steady, so the partial differentiation of the velocity vector with regard to time is zero. Here, the flow is considered as incompressible, so the fluid density ρ is a constant. However, compressible Bernoullis equation is possible, for instance, for the ideal gas, but its applications would be limited to some very special cases. The body force is conservative. Generally, the fluid gravitational force is the only body force. It is a conservative force, and it can be expressed as in this form. And the flow is on a same streamline. See here, the streamline in the pipe. So the conventional Bernoullis equation would be given in this form. Here, vector v is the velocity vector, p is the fluid pressure, rho is the fluid density, and g is the gravitational acceleration. Here c is the integral constant. For the application in the pipe flow, we have the expression for the Bernoullis equation as this. Here, subscript 1 means the parameters at the section A1, and subscript 2 means the parameters at section A2. At this Bernoullis equation, we can build the relation between the fluid velocity and the fluid pressure. We will see some examples for this application.